Welcome to this lecture series in linear algebra. In this lecture, we want to see some interesting examples of minimal polynomials. In the last lecture, we just saw one very measly example, but in this lecture, we want to rectify that. And in fact, we'll see that every monic polynomial occurs as the minimal polynomial of some endomorphism. So that's a very interesting observation, actually. And let's just recall what is the definition of a minimal polynomial. So if we have an endomorphism on a vector space V, then we say that a polynomial, suppose we have a polynomial Px, let's say it looks like that. And we say that T satisfies P if Pt is 0, meaning if this endomorphism is the 0 endomorphism, and it so happens that given any endomorphism, there is a unique smallest degree monic polynomial that is satisfied by T, and this unique monic is called the minimal polynomial of T. So there is a unique smallest degree monic polynomial which is satisfied by a given endomorphism, and that is called the minimal polynomial of the endomorphism. Okay, so with that, let us proceed. So here is our first example, or I don't know what you want to call it. So fix this polynomial x squared plus x plus 1 over the reals. The question we are asking is there an endomorphism on some real vector space whose minimal polynomial is the one that we have chosen? So the answer is yes, and we will construct such an endomorphism. Try to do it yourself before we look at what I'm going to show. Okay, so why is this? Let V be this two-dimensional vector space. So this is a two-dimensional real vector space, and choose a basis. Choose a basis of V, and in particular, of course, you can take U0 as E1, the standard basis vector E1, which is this guy, and U1 as E2, which is this particular vector. So you can take that. Okay, and define an endomorphism on V via the equations Tu0 goes to U1 and Tu1 is this guy. So it's unclear why are we defining it, but you'll see. So I claim that this endomorphism has Px as its minimal polynomial. So let's see why. So first of all, we'll show that T satisfies Px, and to do that, we compute this guy, which is nothing but T of U0, which by definition is this, which is, let me write it the other way. Okay, so we have that, and this implies this equation. So if you just shuffle things around here, you will see that this holds. Okay, so once this holds, we also see that T of this thing is also 0, but this is same as that equation, but Tu0 is V1. So we have this other thing also. Okay, so let me shift it a little bit. Yeah, so using these blue things, this one and that one, we deduce this is the case. Because U0, sorry, this is not V1, this is U1. There is no V1. Yeah. So since U0 and U1 together form a basis of the vector space V, and this guy kills both of them, this guy kills every vector, and hence we have this. So Pt is equal to 0. And Pt is obviously a monic, so this is a candidate for the minimal polynomial. The minimal polynomial of t must divide px. Okay. Now, if you observe that px is irreducible, then clearly it just immediately follows that px has to be the minimal polynomial of t. But even without observing that, note that there is no smaller degree polynomial, there is no smaller degree monic polynomial that is satisfied by t. Smaller degree meaning what? Smaller than the degree of this. So if you take a degree 1 monic, you will see that this can never happen. Why is that? Because u0 and u1 are linearly independent. So if you take this polynomial, let's say x plus a, then if t were to satisfy it, then we would have t plus ai is identically 0, and hence in particular this would be 0, which would mean u1 plus a u0 is 0. But that cannot happen because u1 and u0 are linearly independent. So that shows that px is the minimal polynomial of t. So we kind of forcefully constructed the required endomorphism, and just note what is going on here. Just kind of try to observe the pattern. This will be more clear in the next example. So here we have taken some different polynomial, a little bit more complicated if you will, and we are asking the same question. Is there an endomorphism on some real vector space whose minimal polynomial is same as px? And let me just define what is that endomorphism. There can be many, but we will construct only one. So again, we have this vector space, and we choose a basis, and now define via the equations. tu0 will again be u1, and tu1, if you look at what we want, if you look at this polynomial and look at what I'm going to write, it is that thing. You define it that way, and then you'll see the same thing. So you'll see that t square plus 2t plus 7 of u0 is 0, and this will automatically imply that this is also 0, just like in the previous example. And again, this shows that pt is 0 because it kills both the basis vectors. And again, as in the previous example, you can show that a degree 1 monic will not do. T will not satisfy any degree 1 monic. So that's it. So I mean, once you have the polynomial in front of you, you can explicitly write down such an endomorphism, meaning an endomorphism whose minimal polynomial is the given polynomial. Okay? And let's take one more example. This time we have a degree 3 polynomial, and we are asking the same question. Does there exist an endomorphism on some real vector space whose minimal polynomial is px? So in all our examples, I'm using real vector space, but you can do whatever you want. You can pick whatever field you like and pick a polynomial over it, and you can construct the required endomorphisms in exactly the same way. So again, let me just write down what is the endomorphism here to finish this lecture. So this time we'll take a 3-dimensional vector space and pick a basis. And now just define the endomorphism via the equations. tu0 is u1, tu1 is u2, and tu2 is minus 4u2 minus 7u1 minus 3u0. Just look at this part and that part, and you will see what is going on. So yeah, and make the computations, you'll see that the correct thing happens. Meaning the minimal polynomial of t is this guy. Okay, so with that I want to end this lecture. Yeah, before I end this lecture, let me just emphasize that what we have really done is show that given any polynomial given any monic polynomial over any field, you can construct an appropriate endomorphism on an appropriate vector space over that field whose minimal polynomial is the given polynomial. And there are many ways to do it. I have just done it in one possible way. This is not the only way to do it, of course. And now with that, I want to end this lecture. As usual, like, comment, share, subscribe, and I will see you next time.